Hello everyone, I'm Paul Steciuk with Northeast Power Systems, and welcome to this EasyPower webinar. This is an open mic session, and what that means is that if you have questions, you can ask those questions. This is the first time we've done this, so bear with us if we have some technical problems. If the mic does not work, then we will have to work through the questions board on the WebEx or the GoToMeeting app here. So I'm Paul Steciuk with Northeast Power Systems, and just a little bit of background. I've been doing power factor correction, harmonic filtering, designing medium voltage harmonic filter systems for nearly 25 years. I have some background in the low voltage systems also, but basically my career has been dedicated to the design, construction, application, and analysis of harmonics and on medium voltage systems, more or less, and also the design of harmonic filter systems associated with them. So I have quite a bit of background knowledge on this material, and the purpose of this session is to answer questions that you might have. I'm going to come at this from an angle of a real world experience. And tell you if I feel that something isn't, if I haven't seen it in 25 years, I believe to some degree it may not be important or it may not be something that has to be looked at in detail. So I will address each of the questions. So if you have questions regarding power factor correction on commercial, industrial, or utility systems, design specification of harmonic filters, component specification and application, and this is in regards to the design and construction of harmonic filter systems, or if you have application questions, then I think I can answer those questions. I have been using EasyPower for nearly the same amount of time, so I have quite a bit of experience in the harmonics module of this software package. So in advance, we have asked questions. I think we have a good 20 questions that have been already asked. I have tabulated those questions here, and I'm going to just address each of these questions one by one. And as I'm discussing these questions, you may come up with other questions related to the topic that we are discussing. Feel free to chime in this regard and ask your question. I can then try to address those. And if not, then we will move on to the next question. So in advance, we had the first question is there a mathematical formula I can use to determine the effect of the harmonics as on power factor using variables that are typically available in power system analysis? So let's go here. So I think what is being asked here is the difference between displacement power factor and apparent power factor. And in the world that I've been working in, displacement power factor has been the key power factor of concern. Displacement power factor is associated with the fundamental 60 hertz or 50 hertz power factor. Is the phase angle shift between voltage and current. It's the amount of reactive power as measured at 60 or 50 hertz, or the fundamental frequency that is of concern. And to my knowledge, it is also the primary component of what is penalized by the utility. When the electric utility is talking about power factor, they are talking about displacement power factor. It has nothing to do with harmonics. And in the past 25 years, again, I have not had to enter into what is called true power factor, and I show that down here. And true power factor being related to the power factor associated with the 50 and 60 hertz values, the fundamental harmonic, the fundamental current or fundamental voltage, but it also includes the effects of harmonics. So with an increasing in harmonic currents, there will be a decrease in power factor. You are drawing more what I would call unuseful power from the network, and that unuseful power is going to come out as a poorer power factor. But if this is a topic that is of concern or that you want to dig into, just by doing a quick search on the internet, I have found lots of information about displacement power factor and true power factor. But I think in the world of power factor correction, harmonic filter design, and in places that I have been involved with, I have not really seen true power factor to be something that I deal with very often. So on to the next question. On 480 volt facility distribution system, what is the maximum or expected range of THD? In my experience, I have always used 519 as a measure of allowable harmonics. And what's important here, I think, is to consider is that, you know, IEEE 519 does provide harmonic voltage distortion recommendation of 5%, and they have harmonic current distortion values at the point of common coupling. This standard, you know, represents a number. It's not necessarily a number where things fall apart. And it's been my practice that when I do designs, harmonic filter designs, and I'm trying to mitigate harmonic distortion, I use 519 as a basis, as a desire to achieve that level or better. Within the facility itself, there are no harmonic current distortion limits, right? You're inside the facility, you're not at the point of common coupling. So within the facility itself, there are no distortion limits. So there you're looking for the best practice, and applying 519 is a reasonable practice to follow. If you exceed 519, will you have a problem? No. And now the same goes for voltage distortion. I design a harmonic filter system, and I am looking to achieve of at least a 5% or better voltage distortion throughout the entire plant. If you get to 6 or 7 or 8% voltage distortion down at the 480 volt network, and sometimes it's difficult to get down deep into a network where you might have a large VFD drive pushing distortion up. Unless you put a filter at that drive, you may have a difficult time achieving 5% voltage distortion. But this is your target, and you're just trying to design an entire system to have good performance, to not have power quality issues. So using that 5% voltage distortion throughout the plant, whether it's the medium voltage network or the low voltage network, is a good number to shoot for. I have seen, however, plants running at 10 and even 12% distortion and not have any types of issues. Another key thing to remember is that voltage distortion affects all loads in a system. So when you have high voltage distortion within a plant, you're impacting all electrical loads because they are connected in shunt with the network. They are seeing that voltage. So voltage distortion is a key design parameter when designing your network, and 5% is a good target number to start with within the network itself. The next question is, how do we calculate the size, and this is the kVAR rating of a harmonic filter. So in this regard, I have a slide here that goes through the design calculation for a notch-tuned harmonic filter system or harmonic filter, and this is for a 13.8 kV, 500 kVAR, 4.7 tuned harmonic filter. So typically, the way filters are designed is you're looking to achieve a power factor within a facility. The filter's primary rating, one of its key ratings is kVAR or megaVAR output. So very often filters are put in for power factor correction. When that is the case, the first design concept is to ask yourself, well, what power factor am I trying to obtain? How many VARs, how much reactive power do I need to obtain that rating? And then from there, you design your filter. And that starts off with this Q effective value here in the top left. So I won't go through these equations one by one, but what's key here is that once you do design a harmonic filter, you have to look at the voltage on the capacitors, the current on the capacitors, and also the current on the reactors. And we have a general rule of thumb here in that we designed a filter such that the harmonic current does not exceed 50% of the fundamental current rating of the filter. and this is kind of a key design concept. So if you have a lot of harmonic producing loads within a facility, your reactor, okay, X of L here, has to be able to handle that harmonic current. And the capacitor down here, per IEEE standard 18, also has to be able to handle that harmonic current. And there are limits on that, on those values. So you have to come up with a Q effective value, put this harmonic filter design into your EasyPower analysis model, and then evaluate the amount of harmonic current that actually flows through X of L and X of C, and evaluate that against the standards. The reactor is a custom built device, whether it's medium voltage or low voltage, that can be a custom built device. It tends to be that low voltage systems, the reactors are a standard off the shelf design, and they do have a limit in their rating. So you have to evaluate how much current flows through that reactor versus its rating. And the same will be true for the capacitor. But our general rule is to size the filter system such that the harmonic is 50% of the fundamental. And then we rate the harmonic filter for 100%. So we give ourselves an additional 50% margin. And this is key. To make sure that you have margin in your design, because there are always the unknowns that get you in this with these filter systems. On our website at www.nepsi.com, we have some spreadsheet tools for designing harmonic filters, and there are three major types of harmonic filters used. There's high pass, C high pass, and there's notch filter. We have a spreadsheet tool that is used and made available to consultants, whoever would want to use those. They are available for your use, and they help to evaluate the values of X of C, or the value of the capacitor in a reactor, and come up with the correct design parameters based upon tuning point. So I would suggest that you consider going there. It's under the resource page on our website.
Paul, this is Jim.
Yes.
We have a follow-up question on your first slide. It's from Rebecca Yitna, and the question is, if the voltage limits of 519 are met, but not necessarily the current distortion in the limits, is that a problem?
The distortion values are met, but the current distortion values are not.
Correct.
And I would say that within the plant itself, it is not a concern. The current distortion is not of concern. There is nobody evaluating that. Of course, if you have higher harmonic current distortion within the plant, you will experience more heating in the transformers and things like that. But this may be minor. I think of major concern is actually what of major concern is what is the voltage distortion, because that's impacting the rest of the facility.
All right.
So next question. Okay, is there a difference in calculating or calculation determining the size of a bigger load? Example, electric arc furnace as compared to smaller loads. And I say that the answer to this question is that you must be more concerned about those larger loads, the arc furnaces, the large VFD drives. When you have many small loads on a facility, those small loads have varying phase angles. You have more cancellation. So the impact of the small harmonic producing loads are not of concern as much as those large loads. So if you have 1,000 horsepower or 2, 3, 4, 5,000 horsepower VFD drive, you must certainly model that and be more concerned about the impact of the harmonics related to that device, because the true output of that device will be what your facility sees. When it's a bunch of small devices, those loads, although they could add coincidentally, they can all be in phase with each other and they can all add. It tends to be that they don't add directly. So the impact of the many small loads is much less than the impact of one large load. And it's very typical that from my view, I always ask for the very large VFD drives. Tell me what the large harmonic producing devices are, and those get modeled and I concern myself less with these smaller loads, computer loads, incandescent lighting, things like that. I'm typically not as concerned with, especially at the medium voltage level. So I think I answered that question, but okay, so I will read this next one. Question number one, this person had two questions, because that says, I'm not sure our campus needs to invest in adding harmonic module and EasyPower. Can you talk through how we can try to determine if such an investment is something we should be pursuing? In other words, how to sell this service to a typical client. Right now, our central power / chilled water steam plant has good power factor between 0.92, 0.95. And I'm not being told by operators that there's much concern with Harmonic's high current, but they may not know what to look for, and I could use some help in this regard. So remember that the Harmonic Analysis software is used to evaluate harmonics within a facility, but more importantly, it's used as a tool to determine or predict what would happen if a change is made in the network. So the analysis tool, I would call this, is to evaluate what if on a system, or to evaluate what might be causing problems on a system. So if you're not having problems on a system, it may be something that you will be able to sell that easily. But if you are planning to make changes with any system, this is what this tool is used for, is to evaluate what that change will be. And it would be very difficult to evaluate the change without having a tool like this Harmonic Analysis package. So a simple change such as adding a capacitor bank to the network would be an example of something that would suggest that you should go out and purchase the software package so that you could then evaluate the impact of that capacitor bank on the network. The installation of a large VFD drive would be another case. But when you have a facility that's not experiencing problems, I'm sure that your boss will ask the question, well, what's the payback? And you may not be able to justify it in that regard. Okay, so the second question, if a company is going to invest in harmonic monitoring, what is the basic pieces of equipment that would be needed to completely assess the big picture, data logging, fluke meter, etc., along with the EasyPower Harmonic Analysis software module? If there are pieces of equipment that we need to be ready to utilize, please advise. So I typed in red here what I would recommend for the purpose of assessing harmonic levels. The harmonic metering device should comply with these two IEC standards. So the new harmonic standards use statistical analysis, and they group the harmonics into statistical data sets based upon long-term and short-term measurements. So you want to have a device that's compliant with the new IEEE standard 2014, which basically follows these two IEC standards. So that would be the only device that you really need, would be a monitor that can monitor in accordance with these two standards. Okay, so next question. What do we need to model equipment, rooftop units, package equipment, VFDs, LED lighting loads, panel loads with computers, etc.? So this is a modeling question. When you model harmonic load, and I guess I would jump over to EasyPower real quick. When you model harmonic load in EasyPower, and what I've done is I put a load on the bus here. That's simply done by grabbing the load over here and double clicking the load. And the harmonics tab shows the input requirement, and if you have a harmonic, you click the harmonic button there, and from there you have to put in some kinds of values. The tab itself is looking for harmonic number and harmonic current percent here, and you're actually modeling the harmonic current injection that device puts out. So if it's it's a VFD drive, you need to have the harmonic current values, and You know, often I just put in 100 amps there because this is looking for percent, and then from there I can put in the actual harmonic current. So it might be fifth harmonic. I might have 10 amps of fifth for that device, and then 3 amps of seventh, and so on. So you need to know harmonic number and harmonic current output, or harmonic percent. And if you put into fundamental amps here at this tab, you would put in the percent harmonics here for that device. If you know the amps, then put in 100 amps here and just put the value of amps there. And that's the typical way that I model harmonics, is actually real current injection for those devices. There are other ways of doing this. You can also do this on the motors tab. You have a harmonics tab too. So all of the individual loads within EasyPower have the ability to put in a harmonic current injection for that device. I tend to sum up the total harmonics and put it into a harmonic load as shown here. Right? That's my preferred philosophy. Sometimes somebody might have gone out and taken measurements at the point of common coupling at the main incoming of a small system like this. Those measurements I would then put into a load down here, and oftentimes it may be 0 megawatt load like this, a 0 megavar load like that, and then I have just harmonic current input. So it does not impact the load flow analysis. It only impacts the harmonic analysis package. So there's a couple different ways of doing it. But again, if somebody's taking measurements, you can put that on the bus as a single point in current injection, and not bother modeling all these other devices within the system. So it depends on how you're receiving the data. It's quite a bit of work to go through a facility and model each individual load in a facility. That's a lot of work, and in the end, I don't really know what the value of that is, because these devices, when you have multiple devices on the same bus and they're operating at different speeds, different load levels, they are putting out harmonics that are at different phase angles, and the net result is that it's not completely additive. There is a degree of cancellation of those harmonics, and therefore putting a harmonic current injection associated with each load and every load on that bus may give you quite a pessimistic result. And doing a harmonics measurements at the point of common coupling might make more sense. Okay, so next question. I have an application where I have harmonics coming back into my system from a switching source. The switching source has 2 feeders, 400 amp, each with 100% resistive loads. Can I put one side on a delta, one side on a Y transformer, and the other on delta Y? So we're actually talking about doing delta Y and delta transformation for a load. This is typically done with a VFD drive, where you're taking 2 6-post drives and you end up with a 12-post device. All right. So in this case, the person is looking to create a phase shift on the sine wave, which should reduce harmonics. So my answer to this question is putting delta Y and delta transformer in makes sense when you have 2 devices that operate at the same phase angle, same load level, and so these devices must have some kind of they must be synchronized with one another. If you have 2 drives and they both operate at different speeds, to put one drive on one delta and put the other one on delta Y, if they were operating at different speeds, they are also operating at different phase angles, and the net result is they may still add even when pushed through a delta and a delta Y transformer. I had this picture here just to show you what the harmonics look like on a phase angle control device, which I think this question relates to maybe resistive heating. And you can see that depending upon the phase angle of operation, there are significantly different levels of harmonic current injection by that device. So a VFD drive would be similar. I think if you did a quick search on the web and looked at phase angle versus loading level for a VFD drive, you would find other types of plots like this that would show harmonic current amplitude and phase angle to change quite a bit based upon loading level. Okay, next question. What techniques are there for mitigating harmonic interharmonics, for mitigating harmful interharmonics? Similar what can be said about subharmonics. So the most common thing to do for interharmonics is to put in high pass and C high pass filters. So first of all, an interharmonic is a non-integer harmonic. So you might have a harmonic at the 5th and the 7th, the very common points. You have 5th and the 7th harmonic. There are some devices like cycle converters that would put out a 5.5 or 6.0 harmonic or 6.5. So we're talking about harmonics that occur at non-integer or non-typical values of harmonics. So the typical harmonics are 5th, 7th, 11th, 13th, 17th, 19th, and so on. Some devices do put out interharmonics that are of concern, and usually the technology that's used is to employ high pass harmonic filters and C high pass harmonic filters. And I will just put up a slide here real quick and show the high pass harmonic filter. So here you can see a high pass harmonic filter has a resistor in parallel with a reactor. There's also what's called a C high pass filter, which has a resistor, about a reactor and a capacitor. So the interharmonics are cured with this C high pass and high pass harmonic filters. And I think I can best explain it on this next slide. That might show a comparison between notch filter application and a high pass filter application. So here I show an impedance scan for that situation where we have a notch filter application and high pass filter application. So the red diagram represents the high pass harmonic filter system. The blue impedance scan represents a notch filter system. So here you can see that for notch filters we have these peaks, these blue peaks here, and they represent actually resonant points caused by the next tuned filter up. So if you have interharmonics, and that's what you see here, if you have an interharmonic, say here at the 6th here, if you had one, it would result in a high distortion. So installing a damped filter, a high pass filter, or a C high pass filter will help to eliminate these resonant peaks that exist between tuning points in a harmonic filter system. And in so doing, we get this red curve. Okay, so a C high pass and high pass filter has more losses, and but it does not have the resonant peaks that a standard notch filter system has. So what I'm trying to say here is that to eliminate the concerns related to interharmonics or the non-integer harmonics, you would typically use a C high pass or high pass filter. And there's a question about subharmonics, and this is something that I don't know the answer to, the subharmonics issue. I got a feeling this is a sub-synchronous frequency, sub 60 hertz or sub 50 hertz, and I think that's what this question is related to. That's a different problem than the interharmonics. I think this sub 60 hertz, sub 50 hertz issue is more to do with system dynamics, and is something that I have not been involved with, so I can't answer that question. Okay, so next question. IEEE 519 limits for both THD and TDD are to be applied at the PCC, where plant facilities interfacing with the utility, and a huge plant where there are several sub-plants or sub-facilities are involved. Here, where each of these sub-plant, sub-facilities are part of the individual project, is it safe to consider to apply the same limits at the interface of these individual sub-facilities to the overall system of the plant itself? I think we kind of addressed this earlier, this question, and I think it also applies here. The real limit that you're trying to meet to meet and interconnect with the utility is at the PCC, but you're to take a philosophy of designing an overall system that is power quality is free of power quality issues. That might be a good practice is to bring that PCC into the network and also look to achieve the Harmonic 519 limits at the individual what you deem as PCCs within a facility. So I would certainly say that that's not a bad practice is to look at putting the PCC within the facility itself, multiple PCCs. IEEE, not IEEE, but EasyPower does allow multiple PCC points within the network. You can assign a PCC to any of the breakers or switches within your network and do a 519 calculation table for each of those locations. So that's certainly something that I would think would be a pretty good practice. And then again, looking to achieve 5% voltage distortion throughout the entire facility would be another design objective. Okay, next question. If we can't apply the limits in IEEE 519 to the individual plants, how can the harmonics be evaluated for each of these individual plants when conducting silo studies? So I think you can apply 519 distortion limits. It's not going to be a requirement by your local utility, but again, it's just a good design practice to do so. Okay, I'm wondering how to simulate the generator AVR mode, i.e. voltage droop mode, power factor, or INVAR mode. So this is something that I'm not sure what this question is about. I do not think it applies to the harmonic analysis module within EasyPower. This generator AVR mode, I'm not even sure if it's in the load flow portion of the program. It may be only in the dynamic analysis section of the program itself. So I can't answer this question. I don't think it relates to harmonics in the context that I've been dealing with. I've not ever had to do generator AVR modeling or analysis. So I'm not the appropriate person to answer this question. All right, I repeated that question by mistake. Next question: why does harmonic current represent flow represented to flow towards the system, whereas harmonics generator and inverter UPS draws the current from the system to supply loads? How can a device draw current from the source, but also give current back to the system? That's a good question, and on the surface, it's I guess it's hard to conceptualize. I have always modeled harmonic loads as harmonic current injection devices. I have a feeling this goes back to the Norton equivalent, and where you have a 60 hertz voltage source, and then you're modeling the current injection at the other harmonics using a Norton type equivalent. That's the best I can answer this. It's a little bit into the theory of the modeling, and again, that's not my area of expertise. Okay, next question is, what does it mean by 1 per unit harmonic injection as featured in EasyPower, and when to use it? So I'm going to pop up the EasyPower screen again, and first of all, on the lower left here, you should note that there is a system base MVA noted, and in this model, I'm noting that it's a 10 MVA base. So this is this question, I think, is related to the per unit system and what does 1 per unit harmonic mean. So I will first say that you do have to have an understanding of the per unit system to be able to answer this question. And remember that per unit current is defined at each voltage level within the network. So at 138, there is a 1 per unit current. At the 13.8 kV level, there is a 1 per unit current. So since this is a 10 MVA network, this 13.8 kV system would have a 1 per unit value. Okay, 13.8. You would just take 10 MVA or 10,000 kVA, divide by 13.8, and then divide that by 1.73. You would come out with 418 amps. That would be your 1 per unit current level. And that's true whether it's a harmonic or it's the fundamental current within the plant itself. It's 1 per unit current. So EasyPower does allow you to put in current as or to display current as 1 per unit current, or you can display it as amps, or you can display it as the result as you can display it as percent of the rating of the equipment. So at various locations there are references to the per unit, and I'm going to attempt to show you a couple here. I go to Harmonics and Harmonic options. You have magnitude here. So under the control, you have what's called magnitude, and I typically use amps here. Okay, so and this is for impedance scans. This is an impedance scan section, and you're saying, well, what is my current injection for an impedance scan? And if you use amps, then you're going to be injecting 1 amp into your model. You can have per unit here. In this case, it would be 1 per unit. So if you can look at this, if you're injecting 1 per unit current here, you'd be injecting 418 amps. Okay, that would be a lot of harmonic current. If you're injecting amps to develop that impedance scan from this location, you would be injecting just 1 amp. So the impedance scan is developed based upon whether it's based on amps or based on per unit. So with that being said, it's also important to realize that we also have per unit here too. So the current flow in the text outputs can be either in amps or in per unit. And remember, it's going to be per unit on a system base, and then again per unit on equipment rating base. Okay, the rating of the conductor, the rating of the transformer, etc. I typically always use amps because I can relate to amps more than I can relate to per unit. I think 1 per unit is difficult to relate to when it comes from a harmonic analysis standpoint. From a power flow standpoint, 1 per unit makes a lot of sense, because 1 per unit power flow means you're at the rating of the equipment. If it's based on the equipment rating, or 1 per unit based on the base rating of the system. If it's 10 MVA and your devices are already 10 MVA, then it kind of has some kind of measurable feel to what it means. And then plot output, here you can plot the branch current either in amps or in per unit. So it's key to understand what that per unit means. I think I answered that question. I think I got this question repeated again, so we'll skip the AVR question. Again, I don't think it's something that goes with within the context of the harmonic analysis. What I can say though is in the real world, where we have seen one project where we had a tap changer. It's not quite a voltage regulator in terms of a generator, but we had a tap changer that did have a lot of issues related to a high frequency voltage distortion within the facility, and the way we corrected that was through a high pass harmonic filter. So we did see some sporadic operation of a tap changer that was regulating voltage, and it was having issues because of distortion. So it can impact it. If this is an equipment issue, I would suggest that you contact the company building the voltage regulator. Okay, so the next question is, can there be an example calculation for harmonics, and also how can we resolve it during the webinar, during harmonic and after resolving scenario, and also demo using EasyPower? So here I would suggest, because it's a pretty long presentation, I would suggest that you consider going to another EasyPower presentation that I did a couple years ago. It's at this address here. It's actually a two-part presentation on using EasyPower on a very, very simple system. I would recommend that you consider watching that. I also think it's very important that you have to be able to do your harmonic analysis on a simple system on paper, and then to be able to repeat that using the EasyPower software. Being able to do that helps to ensure that you have your system modeled correctly, and that you actually understand exactly what the program is doing. Once you can go beyond a simple system on paper and replicate that within the analysis package itself, and then a more advanced system, you will know you're not making mistakes, and that you understand the output of the results that the program is giving you. So that video or webinar that was produced a couple years ago does go through an example that can be done on paper and then replicated within the program itself. How to actually interpret a frequency scan result. Again, I'm going to say consider watching those two videos. Those two videos were part 1 and part 2 did get into this, and since we do have a little bit of time, I can get into this briefly also right now. So when what you see here on the left is a very simple system that's been modeled in EasyPower, just a source, a transformer, and then some loads. The equivalent network for this system here is shown on the right. You can see there's a source impedance and a transformer impedance. And then we have our harmonic current injection to the right here. Remember, that's an ideal current source, which means that no matter what this impedance is, this current flow will be pushed through that impedance. Kind of like a current transformer on a network, CT will push out secondary current no matter what its impedance is up to a saturation point. An ideal current source will push out harmonic current or current to the value that's specified. So I take this system here and I convert to impedance values, and I did it in ohms. You could do it in per unit, that the system can boil down to just a single current injection and a single impedance. And in such case, you can inject 1 amp, okay, at each frequency and create a plot, okay. And it will be, if you have 1 amp of injection, you have V equals IR, right? You have R equals V divided by I. If I is 1, the resulting voltage at this point actually represents impedance also. So if you were to do a plot, it would be just a simple linear curve like this. And so when the systems get more complex, and this is harmonic number versus ohms on the axis. So this is the most simple impedance scan that you can have. And it just basically says that what the impedance is for each harmonic current point on the network. When you add a capacitor, the capacitor, remember, varies based upon X of C divided by N, X of C being the capacitive reactance of the network. And that capacitor's impedance curve looks like this. And it's a green curve. So as the harmonic number goes up, the impedance drops off. So you end up with two different types of responses to harmonic current between a capacitor and a reactor. So when you have a system that that includes both a capacitor and a reactor, you end up with a resonance. And this is an impedance scan that actually shows a resonance system, a resonance. So the pink curve represents resonance, and the x-axis again is ohms. The y-axis is x-axis is harmonic number, excuse me, and the y-axis is ohms. So if we were to look at this curve and just look where I have the arrow pointed, that's about the fifth harmonic. And at the fifth harmonic, if I were to inject just 1 amp of current, and this is the key here, if I were to inject just 1 amp of harmonic current, this network would experience nearly 550 volts of harmonic voltage distortion. And that's line to neutral voltage distortion is what that's reading. So when you get an impedance scan generated by EasyPower, if you have it set up correctly, on the left axis you will have you can have ohms, and on the I'm getting these axes mixed up. On the y-axis you can have ohms, and on the x-axis you can have harmonic number, and each point on those curves represents the resulting voltage for 1 amp of current injection, which is interesting, because if you have a device that puts out 5 amps, then the resulting voltage is 5 times that value. And in this case, it would be nearly 2,500 volts for just 5 amps of current injection. So you can see where resonance is an issue here. So this is one of the key ways of interpreting the impedance scan. The other thing to realize about these impedance scans is that you could potentially look at this impedance scan and say, well, I don't have a 5th resonance and I don't have a 7th resonance, and your data that would be put out by EasyPower in the, say, the IEEE 519 table that it puts out, it would show that your distortion actually might not be high. But by viewing this impedance scan, you would say, oh, well, I got a resonance near the 5th, got a resonance near the 7th, but it's not on the 5th or the 7th. And in this case, you would have concern, and your concern would be, well, if a slight change in system impedance were to occur, say the short circuit level was higher or lower than what I modeled, then I could potentially have a 5th resonance in the 7th or a 7th resonance. You get a picture kind of shifting this curve from where it's located, which is at the 5.59, just shifting it to the left to near the 5th, and so shifting that impedance curve just by a little bit, you can have a very significant change in your results. So a system like this would be an example where the results might show it's okay within 519 limits, but doing some perturbation analysis, changing the impedances just a little bit, you can picture that curve shifting to the left, causing a resonance and then resulting in high distortion. So the impedance scan is used to evaluate, and it's more of a judgment call. What can a small shift do to the results? Can I enter into resonance? Are there harmonics at that location or near that location that I'm concerned with? These are the types of questions that the impedance scan can answer for you.
Paul, we have 4 questions coming in online.
Okay.
Do you want me to read them to you?
Let me see if I can. Yeah, maybe you should. I'm having trouble. Yeah, why don't you read them, James? I'm having a little bit of trouble getting it right here.
All right. The first is from Rolando. He's got a question as a follow-up to the first slide that we discussed. And he says, why would the current limit violation not be a concern when IEEE actually provides this limit? Why then is there a current TDD limit when it won't be a concern?
Well, because, so first of all, the total distortion limits defined by 519 are defined at the point of common coupling. So within the plant, there is no definition of that TDD value, and therefore it's not a concern, because there's nobody that's twisting your arm to say, well, you need to be at that limit or better. When you're at the point of common coupling at that location, you basically have a contract with your utility that you're going to clean up the power that you're messing up with your your nonlinear loads. And there is a requirement to meet a contractual requirement between you and your customer. Within the plant itself, there's no contract requirements, and the main concern is, are harmonics causing issues within the plant? And you can very easily be over IEEE 519 limits as provided by IEEE 519 and not have problems within the plant. So within the plant, I tend to stick with trying to obtain 5% voltage distortion or better throughout, and not concern myself with trying to meet TDD limits within the plant. And additionally, it really is a misapplication of the standard to take 519 and apply it within the plant environment itself.
Okay, makes sense to me. The next question is from George Garcia. He says, hello, in EasyPower, when you insert a filter in the data tab, it asks to insert a value of R for the inductor. What are the typical X over R ratios for medium voltage reactors and low voltage reactors?
Okay, so I can, so in EasyPower itself, there is when you do, I'm going to kind of just expound on it a bit. When you put a filter in, the question is right here for a notch filter. It's asking for ohms, J ohms, which is inductance, right? That's inductive reactance in ohms. And then it's asking for a value of R here. And our philosophy, my philosophy here is that for iron core reactors, I assume a value of X over R equals to 100, which is nice. So when I got a 4.5 ohm reactor here, 4.5 as X, which really defines the tuning point of that filter. I just put 0.045 here, so it's very easy. Air core reactors, there's more conductor within an air core reactor because they have to form that inductance in air rather than with the iron core and having gaps within the iron core. So there's much more conductor utilized in an air core reactor, and as such, the resistance goes up in air core reactors. So for air core reactors, we typically use an X over R 60. So 60 for air core and 100 for iron core would be my starting point. And from that standpoint, the analysis is not impacted significantly if your numbers change from that, and as you move forward in the design of your filter system, you will see that changing R will not make a significant difference in the performance of the filter.
Good.
Right. Yep.
So this is a question that's actually been proposed to me on multiple times, and that is from Brian Myers. Are there common physical signs or basic what to look for symptoms that signal within a facility would make one suspect that harmonics or low power factor are a problem? Okay,
so there's a lot of questions packed into this one question here. You are answering the question: are there common physical signs or basic what to look for type signals, right?
Right.
Jim, that's the one. Okay, so poor power factor within the facility, number one, typically causes voltage drop within the network. So if you have a system with poor power factor, the voltage regulation throughout the network is poor. And what that means is that before the load comes up, the voltage may be high. As your load comes up, say people come in for work on Monday morning, the poor power factor loads would tend to pull the voltage down. So having low voltage within the facility I would say would be the first sign of poor power factor. Another sign of poor power factor is on your utility bill. You may have a power factor penalty. This is sometimes would take some studying because not always is power factor billed with the term power factor. Sometimes it's billed using kVA, and on your utility bill there's typically a kVA demand charge, and then there's the energy charge. So paying attention to your kVA versus your kW load within the plant is another one. For a good power factor, you want kW to be nearly equal to kVA. In terms of harmonic issues, with what I have seen is that harmonics tend not to be a problem until some type of capacitors are installed. It's almost always the case that it's the capacitor banks within facilities, in my experience, that cause problems. The facilities, most facilities can handle a significant amount of harmonics without issue until the day a capacitor bank is installed, and it's that resonant condition that really will exacerbate any type of harmonic issue within the plant. So when you do have capacitors in the plant, the resonance issue will show itself as blown fuses on the capacitor bank as most often the cause. Very high voltage distortion, sometimes 20–30% voltage distortion may also show itself. The transformers, if you have high distortion, the transformers will tend to be much louder. It will be another sign of harmonics within the plant. And then, of course, you got the heating effect of harmonics within transformers to look for. If the load is not beyond the rating of the transformer, but yet the transformer is running hot, it would be typically a sign for high harmonics.
The next one from Syed Hassan. He's talking about the example you used earlier on a 13.8 kV system. If he's adding a harmonic load at the lower voltages, can he utilize the measurements from before, or does he have to run another harmonic measurement?
Okay, that's a good question. I got it right here in front of me. So we got this network in front here. We have 138 kV network and a 13.8 network here. So if he has old measurements and there has not been a significant change in the harmonic injection within the plant, in other words, the harmonic producing loads within the plant, then no new set of harmonic measurements is necessary. If you are adding load, I mean, the purpose of the program is to take existing measurements at the point of common coupling and then add that additional load into your model with the measurement load modeled here. So you can of course take your harmonic measurements, model that within the network itself, and then the additional load, which might be a VFD drive, say 1,000 horsepower drive here, you can then add that 1,000 horsepower drive, and then it will be the cumulative sum of those two harmonic producing loads that will result in the performance of the network here. One key thing I think I should mention, that if you are doing measurements and there are capacitor banks in the network like this here, if you're taking measurements here, for your measurements to have meaning, it is an absolute requirement that these capacitor banks be off. So remember, there can be harmonic amplification between the capacitor here and the network here. To take harmonic measurements with the capacitors online at this point would be to be inside that resonating circuit, and your measurements will not have meaning. They could be either high or low depending upon where you are in frequency. So harmonic measurements on a plant-wide basis should be taken while the capacitors are offline. It does have some meaning to put the capacitors online during the measurement, just to evaluate the impact of those capacitors and whether or not there's power quality issues being caused by those capacitors. But if the purpose of the harmonic measurements is to create a system model, the first thing you need to do is take these capacitors offline and then take your measurements.
Next question's from Alexander Novoa. In a normal 6-pulse drive, what phase displacement or angles for the 5th, 7th, 11th, and 13th current harmonics? What happens to those angles if we feed the drive with a delta-delta and a delta-Y transformer? Will those resultant angles for those harmonics or current harmonics be on the high side of the transformer?
Okay, so in this regard, I always model my harmonic sources as being completely in phase. In other words, I do not assign phase angles to my harmonic current injections. But with that being said, when you have a 12-post device, or say it's a rectifier or VFD drive, there is phase angle cancellation between those between the two 6-post bridges within that rectifier, and that cancellation can be modeled outright, or it can be assumed. And in my practice is, if it's a two 6-post rectifiers operating in 12-post mode through a delta Y transformer, is I just model it as a harmonic current injection and not concern myself with the phase angles of those various harmonics. There are locations on the web, if you look for it, you will find those phase angles. But I think it's an exercise that's not necessary. The result is, if it's a 12-post, two 6-post devices operating in the 12-post configuration, then model the 12-post harmonics. That'd be just 12N plus minus 1, right? The harmonic numbers. So that's been my practice, rather than trying to get into the inner workings of two 6-post devices operating in a 12-post fashion.
And Syed has a question that says, as resonance point is changed with the change of the network topology, specifically when you're switching banks of capacitors, how do you decide the exact notch frequency or harmonic filter frequency?
So this is a multi-stage. Let's go here. Multi-stage cap bank, and in this situation, you can see there's a zero line. This red straight line that represents the impedance of the network before capacitors are added to it, and then this purple line represents 1 megavar. The black line represents 2 megavars, and the bright blue here represents 3, and then purple is 4 again. So this is the sequencing or the staging on of capacitors within the network, and you can see in this situation that that you have a resonance that might be over the 5th, and then another one that's slightly higher than 5th towards the 7th, and then so on. So generally, as you add capacitors, you start off at a high frequency resonance, and then the resonant point decreases as a multi-stage cap bank comes online. So the question is what do I tune that filter system to? And really, that's unrelated to the number of stages on. Generally, what is done is that it is always the 4.7th or somewhere around the 4.7th. It might be, some people are going to tune at 4.0, 4.1, 4.7, 4.8, and some will tune at 4.9. But generally, you're going to tune a capacitor bank to be somewhere beneath the 5th harmonic. And the reason you're doing that is that if you look at all these curves, and these represent the curves of a 1, 2, 3, and 4 megabar harmonic filter system, you can see that the tuning point is defined. That does never change. The tuning point will not change. That's a defined point in an impedance curve. And by setting that point there, you have ensured that there is no resonance at the 5th harmonic. You have precluded resonance at the 5th by tuning a filter to the 5th harmonic. But you can see that beneath the 5th harmonic, depending upon the number of megabars I have on, my resonant point has moved down towards the 3rd. The more megabars I put on, the closer to the 3rd I get. But in this situation, the common harmonics are 5th, 7th, 11th on 3-phase networks. And as such, you want to make sure there are no resonances at or above the 5th harmonic, because the harmonics are typically start at the 5th and work themselves up from there. You got 5th, 7th, 11th, 13th. And you can see here that by defining my first filter as 4.7th, I have precluded resonance at the higher frequencies, and as a result, I am not concerned about those. The resonances that do occur as a result of the installation of these harmonic filters are at a tuning point below the 5th, and generally speaking, and this is not always the case, in arc furnaces, for example, there will be harmonics, but generally the case, there are no harmonics below the 5th harmonic. You have 3rd harmonics, but they tend to be zero sequence and also not of concern. So the practice in general should be always to install a fifth harmonic filter, even if there is not fifth harmonic within a network, because it only takes a small amount of fifth harmonic within a network to cause issues. If you were to install a 11th harmonic, for instance, there will be a resonance beneath the 11th harmonic from that filter, and that harmonic could correspond to the 7th harmonic or the 5th harmonic, depending upon the network, and to cause problems. So always start at the lowest frequency and work up from there. Start at the 5th, and if you need to add filters at the 7th, then do so, but you must always start at the 5th.
And Paul, we're starting to run long on time. I'm not sure if you can come up with a brief procedure to carry out harmonic measurements that's being requested by Sachin.
Well, I will go back to that. The procedure should be to monitor at the service entrance. If there's multiple service entrances, then you need to monitor at each of those service entrances. You should model. You should do your analysis with the appropriate IEC instrument for a 1 week period, taking measurements so you get the statistical analysis that's required by the new standards, and do that at each main service entrance area. But while doing that measurement, the capacitors must be offline.
And then the final question is, do you cover resonance or conditions that can be caused by filters?
So first of all, harmonic filters. We go back to this, and what the question is saying is, hey, do you take care of this problem here, these resonance concerns, and here's a 5th, 7th, 11th, 13th harmonic filter, and you can see here this 5th filter causes a resonance beneath itself. This 7th filter causes a resonance between the 5th and the 7th. So these are resonance concerns, and when you have harmonic producing devices that might be at these locations, they are of concern. It's a resonance concern, and the correction to such a system is to put in a C high pass or high pass harmonic filter branches, and that is how you eliminate that concern, is by the use of an appropriate filter. So it's a more expensive filter system, and it kind of comes back to where I was here with eliminating that through a C high pass or high pass type harmonic filter. So that's exactly what you're looking to do. So it'd be this type of filter, or this type of filter, or this type of filter. And it's a damped harmonic filter is what you're looking to do to eliminate resonance concerns by harmonic filters themselves. And it's very common in very large copper concentrator plants that use cycle converters, that these damped harmonic filters be used. Also common in the arc furnace world, where you have lots of harmonics at different frequencies. These types of filters are used, and notch filters are not used.
I think that completes our list of questions. Thank you very much.
All right, great. Thank you, everybody, for coming.